Okay, and we're recording. Guys, bear with me here. A couple of technical glitches today as we get going. I've got to make sure I keep allowing people to enter the classroom. Today we're going to lecture on the sun. I hope you guys are excited about that. I'm going to queue up my slideshow. I'm actually going to queue up my Astronomy 1020 slideshow because it's got a couple of extra images that'll be nice to share with you guys. I hope we're all doing well out there. I've downloaded the lab for today on sunspots. If you guys have a pencil, a ruler, a protractor, and a compass would really help if you have those things. If not, you'll have to just kind of follow along with me the best you can, and we'll muscle through it, okay? Please be aware that those of you who are submitting assignments, thank you, but you got to make sure that I can read the format. Several of you have submitted assignments. It's fewer this week than last week, but several people have still continued to submit assignments that I cannot look at or read, which slows down an already clunky grading process. I don't want any zip files. I don't want any .heics. I want things that I can look at right away and grade. .jpeg and .pdf are the best. And most of you are submitting those.
If it goes into that uploader on Blackboard and it generates an image of it within that like box feature on it, do you see it that way too? So if we can see it good, it's good for you?
I think so. It's hard to know because there's so many of you and I'm getting like so many crazy different formats coming in, but I can see yours, Lucas. I can tell you that because I remember seeing yours.
Okay, awesome.
And like I talked with Chris earlier because I can't remember exactly whether it was a zip file or an HEIC, but it was something goofy. So maybe that's a good point, Lucas. If you can see the image in your loader, then probably I can see the image. So make sure that you can see the image before you submit it, right? Okay, that's something to think about. Otherwise, I can't give you credit for it in the gradebook there just because I can't see it. Okay, it doesn't look like anyone else is in the waiting room. Hopefully if you guys can see who's waiting to be in the waiting room, please inform me of that. I don't know if that's something you guys can see or not. Let's try to get started here. I'm gonna need a black marker. Did we end up on the diffraction limit last time? That's what I remember. Is that what you guys have? Okay. Well, you can now congratulate yourself on having graduated from Baby Physics Academy. And though it took us, yes, clap, clap, Thomas, I like it. It took us a while to get there, but we're finally here and we can start talking about astronomical objects. And I'm not sure just how far we'll be able to get in this very strange semester, but we're going to do our best. So let's start by talking about the sun. I want to start off by just kind of getting you guys excited to think about the sun, and I want to share my screen with you and show you guys where I'm going to be getting some of my images and videos from. So if I can close this here and I can go to my web browser, I want to start by telling you guys about something called the Solar Dynamics Observatory. And if you can see my screen, you'll notice that all I did was type in SDO into the web browser. And the first site that comes up is the Solar Dynamics Observatory. It's an orbiting satellite that orbits around Earth and is continuously imaging the sun, pictures and video, at a variety of different wavelengths across the electromagnetic spectrum. Here on the home page, you see an image of the sun on display, not as it's seen in visible light, the way your eyeballs would see it, but you can see an image of the sun displayed here. I believe this is 193 angstroms. And if I click through the slideshow here, it's a number of different wavelengths showing you the sun at a variety, actually not at a variety of times, all at the same time, which is probably just a few hours ago. This is universal time, 15 hours. We're in daylight savings time, which means we're UT -4. So this was probably taken at 11 a.m., just 40 minutes ago, which is extraordinary. Do you guys remember what an angstrom is? That might be helpful for us here. Let me go into speaker view. Let me lock it on myself. Good notes to start off taking when we consider the sun is you'll want to remember from your electromagnetic spectrum that we often work in units called nanometers, where 1 nanometer is a billionth of a meter. We also sometimes work in spectroscopy in a slightly more archaic unit called angstroms. And an angstrom is a 1/10 of a nanometer, or a 10 billionth of a meter. And that reminds us that, that 1 nanometer is 10 angstroms. So I thought you guys might need a little memory jog on that so that we could talk about the variety of wavelengths the Solar Dynamics Observatory will be using to image the sun. Let me go back to my share screen for just a hot second here. Okay, so class, you can see here that the wavelengths I'm sliding through, these are listed in angstroms. And some of them are composite images of several different wavelengths. Some of them are single images at a single wavelength. Particularly dramatic are the ones that are in the 10s to 20s of nanometers, or 200 to 100 angstroms. Those are on the border of the ultraviolet and X-ray regimes, and they show a different outer layer of the sun, especially interesting when the sun is magnetically active. I want to show you one last thing before I move on. If you guys ever want to poke around this website on your own, you can go to the data section and browse the daily movies. And if you browse the daily movie directory, you can see images of the sun. Actually, they're little movies of the sun at a variety of different wavelengths. So today is April 6th. If we go to April 5th, if we go to April, let's see what we're doing wrong here. Perhaps the coronavirus has kept them from updating it. Let me backtrack a little bit. Oops. Let's go to last year. Let's go to 2019, and let's go to April 2nd. And you can see there's a bunch of different movies here. I'm just going to click on a random one. I'm going to click on the 17 nanometer one. And here you can see a video of the sun over the course of a few hours, showing an active magnetic field and some of these outer wisps of the sun's corona as the sun rotates around. So this is where I got many of my own videos from that I'm about to share with you. I thought that would be kind of nice to start off showing you that. So let's now go to my slideshow. Let me share my screen again, and let me share my slideshow with you. And let's start off by just kind of looking at a single video of the sun taken at visible wavelengths. And that's in slide 3 here. Oop. I'm going to admit more people to the class here. So here you can see an image of the sun taken at 4,500 angstroms. Does anyone in the class remember where in the electromagnetic spectrum 4,500 angstroms is? Where is 4,500 angstroms? Or 450 nanometers?
Is it violet?
Do you mean in the visible spectrum?
Yeah.
It's close to violet, that's for sure, Lucas, but I think there's a color that's better expressed at exactly 450 nanometers. Maybe I can get out another slideshow if necessary.
Ultraviolet.
No, ultraviolet is lower than 400 nanometers.
Is it like teal or blue?
What do you guys see on the screen right now? Do you see my lecture 5 light and telescopes? Oh.
We see lecture 4, the sun.
Okay, I guess I can only share one. I should always share screen rather than the slideshow, because the screen, you'll see whatever I'm doing. Here's the electromagnetic spectrum here, slide 19. What would you describe that color as, 450 nanometers?
Blue.
Oh, come on. That lacks imagination, Lucas.
Indigo.
Indigo! 450 nanometers is clearly indigo. This color has its own unique name. We will call it by what it is. Violet's here, 400 to 430 or so. But 440 to 460 is indigo all the way home, okay? So in any case, the image of the sun that you're about to see in my PowerPoint slideshow. This is 4,500 angstroms or 450 nanometers, clearly indigo light. I wonder why the sun looks yellow in this still image. Does anyone think they know why?
Did they just edit it yellow?
Yeah, that's right. Very good, Kayla. They just kind of made it yellow. They false colored it yellow so that it would feel good to your eyes, to your soul, if that makes any sense. They wanted to sort of impress upon you subconsciously that you are currently looking at the sun at visible wavelengths, and this is what the sun would look like to your eye. So let's go ahead and let's play the tape. Here's a little time-lapse movie of the sun playing at 4,500 angstroms. And here's several hours ticking away at the bottom of the screen. And you can see the sun is in rotation, and the sunspots are rotating along with the sun. These are sunspots here, of course. So there's a couple of different messages behind this video. The first is that it appears to your eyes like the sun is rotating slowly. But one must remember that the sun is a ball which is 1.4 million kilometers in diameter. And that means what may appear slow to your eyes when watching this video is a little bit of trickery, because you're forgetting just how massive and huge this object is. Another takeaway message of looking at the sun at 4,500 angstroms is that the illumination at visible wavelengths, with the exception of sunspots, is quite uniform and steady, and that the sun is pretty much boring at visible wavelengths. It's not doing a lot. You're just kind of seeing this kind of uniform yellow illumination, even though technically it's indigo illumination. By contrast, let's look at that exact same time window. And the video I'm about to show you next is of the same day, the exact same window of time, but instead of taken at 4,500 angstroms, let's click ahead in the slideshow here. Sorry, I'm still admitting participants to our class. Instead, we're going to look at a wavelength around 17 nanometers, which is very close to the border between ultraviolet and X-ray. And I'd like to start off by saying that here, when you see this image of the sun, it looks very different than the one you just saw. You're not actually looking at the same layer of the sun. You're looking at an outer atmospheric layer known as the corona. And let's just play the video so you can see what the sun looks like during the course of that same day near the X-ray region of the spectrum. You can notice massive eruptions on the surface caused by these powerful magnetic field lines threading their way through the plasma of the sun. Over here, in just a moment or two, you'll see something called a solar flare, which is a sort of massive eruption caused by twisted magnetic field lines. And it's hard to impress upon you just how intense that eruption was. That jet of plasma is probably 10 to 20 Earths tall in grandeur. And these sorts of eruptions happen all the time when the sun is in its magnetically active part of its cycle or phase. Today, in year 2020, the sun has actually gone quiet or quiescent. It's at a solar magnetic minimum, so there isn't quite as much magnetic activity on the sun. And the magnetic activity of the sun corresponds to the number of sunspots you see as well. So you won't find quite as many sunspots today on the sun as you would, I can't remember the exact date of this video, but it might have been something like 5 years ago or so. Okay, so I wanted to just start by showing you a couple of those videos to get you excited to talk about the sun and to get you sort of think about what we're talking about. And we're first going to start off by taking down just a couple of basic facts about the sun in our notes. And these are things that I need to reference and you need to know about so we can have an intelligent conversation. Sorry, guys, I'm just going to check my participants one more time. Okay. Two starting facts of the sun are, one, its physical dimensions. And these are numbers that do not change. They're sort of fixed constants associated with the sun. And the other thing that we want to talk about is the composition of the sun. These are just some basic facts that we need to start out with. Okay, so the physical dimensions that parameterize any star are usually the mass, the luminosity, the radius, and the temperature at the surface. The surface is called the photosphere. The mass of the sun is fixed at 2 × 10⁻30 kilograms. The sun's luminosity, its luminous output in terms of light, is also constant, 4 × 10⁻26 watts. And during the course of this week's lecture, we'd like to make note of the fact that the sun's been putting out a constant luminosity for not just a few years, but billions of years. And that's a sort of remarkable fact that this light bulb has continued to burn so constant and so bright for so many years, for the age of our solar system. Also, the sun is a ball of gas and plasma. And weirdly, the radius of the sun does not change. That is also fixed at 700,000 kilometers. Lastly, the temperature at the sun's photosphere, which is something kind of like the surface of the sun, that was that very uniformly illuminated layer that you saw earlier. The temperature at the surface of the sun also remains constant at 5,800 Kelvin. These are numbers that scientists had to do painstaking work to measure, but we kind of need to start off with these numbers so that we can make reference to them and kind of understand just how big and how massive the sun is, how much light it's pumping out. Many other things can be understood in terms of these numbers. Next, we're going to talk about what the composition of the sun is. Now, sometimes people say, like if you like that They Might Be Giants song, the sun is a mass of incandescent gas. And it is true that the sun is a ball of gas. The sun also could be thought of as a ball of plasma. And plasma is a gas. So those two things are not, irreconcilable. But there's a difference between neutral gas and plasma. I don't suppose anyone out there in the studio audience knows what it is. Do you? What's the difference between gas and plasma? Does anyone know? Maybe one of my 1020 students from last semester?
Plasma is charged gas, right?
Charged gas. So the electrons have been torn away from the atoms. Are you guys having trouble hearing? Someone just said in the chat that they're having trouble hearing. Thumbs up if you can hear me. Okay. Whoever chatted that, Zach or Reardon, that might just be, you might have to connect to your audio, or it might be something that you're doing on your end. I don't know. Oh yeah, thanks Parker for adding that comment. Someone help talk her through that, okay? Okay, here, let's get back to speaker view. So the composition of the sun is, it's hydrogen gas, and hydrogen makes up the vast majority, about 70% of the sun by mass. Great, Reardon, glad to hear it. The next most abundant constituent is helium. Helium makes up 28% of the sun by mass, if you can see that. And the remaining 2% is something that astronomers call, weirdly, metals. Although they don't mean what your chemistry teacher means by metals. Metals to an astronomer mean heavy elements, including things like carbon, nitrogen, oxygen, silicon, iron, uranium, whatever. If it's out there in the periodic table, it's not hydrogen or helium. Astronomers call it metals. Metals make up 2% of the sun. Okay, let me elaborate on that point for just a moment here, because I'm a little bit worried that maybe some of you took a chemistry class at one point, and that might sound a little bit jarring if so. somewhere here I have a picture of the periodic, oh shoot. I'm sorry, guys. Let me share my screen again. Somewhere here I have a slideshow that includes the periodic table of the elements. Here we are, slide 16. Function F5, 16. Okay. So if you ever took a chemistry course, you learned at some point that, that you can sort of group atoms into similar chemical characteristics along vertical columns. And that atoms over here on the left-hand side and central side of the periodic table are various types of metals, and that the elements over on the right-hand side of the periodic table, everything that's kind of to the east of this diagonal line, these are all called nonmetals or noble gases or halogens. When you're an everyday person and you think about a metal, you usually think about something like iron or nickel or copper or zinc, or maybe you even think about titanium or vanadium. One does normally, in a chemistry sense, not think of fluorine or oxygen as a metal. But try to understand how an astronomer thinks about things. Most of the universe is locked up in gas contained either in stars or in interstellar nebulae. And the nebulae have almost the same composition as the sun. They're 70% hydrogen and 28% helium. So from an astronomer's point of view, most of the universe, 98% of it in fact, is either this atom or this atom. And all the other stuff represents just a little bit of spice, a little bit of pepper and salt added into the universe. So they just say, screw it. Everything south of those two atoms, they kind of cutely refer to as metals. But you should understand that your chemistry teacher would not feel the same way about metals as your astronomy teacher does. So I want to make that point clear to you guys. I'd also like to make the point clear that just because 2% of the sun is in the form of metals does not mean that those metals are insignificant, at least in comparison to you and me and your pet dog. Let's, for instance, do a quick sample problem just to kind of get the old math juices rolling this morning. And let's calculate what the 2% metals of the sun come out to be in kilograms and compare it to the mass of Earth. Class, I'm going to be erasing here, so shout at me if you're unhappy about that. Okay. Sample problem for the class. What is the mass of the 2% metals in the sun? Someone want to, focus issues here. Someone want to talk to me and tell me what they think the answer to that is? How do I solve that problem?
Put your hand up to the camera so it's a flat surface.
Huh?
And then back it up slowly. Yeah.
Thank you. Yeah, that works sometimes, Peyton. It's if that. Oh no, I'm sorry. That was Parker, right?
Yeah.
Could you divide the mass by 100 and then multiply that by 2?
I guess you could. I prefer to just write percentages of decimals, but ultimately your method, Lucas, would be the same as my method. Just looks a little funny. So Lucas wants to do 2 parts out of 100, which is 2%. That's how I think of the percentages, Lucas. And then you want to multiply that by the mass of the sun, right?
Yep.
Which is 2%. Let's do this without a calculator, Lucas. Do you know how to do that?
I do not.
Okay, so multiply your lead digits.
4.
Okay. What is the power of 10 here?
Oh, so that's moved over
2 places.
2 places.
So subtract
So now
the
it's
decimals.
to the 28th.
That's
Times
right.
10 to the 28th.
Is that greater or less than the mass of Earth?
I have to check.
It's more than the mass of Earth. Let's compare. The mass of the 2% metals divided by the mass of Earth is the ratio of 4 times 10 to the 28 kilograms over 6 times 10 to the 24 kilograms. What's that get you? Work that out for me.
$6,667.
Yeah, 6,667 watts.
Nothing. It's a ratio, right?
Yeah, so what's the meaning of your 6,600 then?
It's 6,600 times larger
Then what?
than the mass of Earth.
Right. Or in other words, it's 6,600 Earths worth of material, right?
Oh, yeah.
If you could extract the 2% metals from the sun and smush them down into a ball or several balls, you could make another 6,000 to 7,000 planets in our solar system. After all, that's kind of like what the solar system is. The solar system is the sun, its gargantuan mass, and the other planets, why, they're like they're part of the 2% metals that didn't quite make it down into the sun. If you could extract those heavy metals from the sun, they don't sound like much, being only 2% of the sun's mass, but you can make 7,000 more planets out of that. That's not an insignificant amount of material, because the sun is not an insignificant ball. It is a massively, stupidly, intensely large and massive object. And it's sometimes hard to comprehend just how big of a structure it is. Another fun trick that we could play too is we could just compare the size of the sun to a sunspot as another mathematical exercise. By the way, I just want to chime in here. I saw someone in the chat screen ask about when class ends today. Class is going to end, the lecture portion will end a little before 1, somewhere between 12:45 and 1. That's the regularly scheduled time. And then we are going to do our lab today on rotation of the sun, as I mentioned. So I'm going to try very hard not to talk over time. I just have to make sure to monitor the clock from time to time. Okay, we'll be doing our homework on Wednesday. I hope that clears up any confusions there. Let's share my screen one more time. And this time I want to try sharing my iPhone with you guys. Let me make sure my Wi-Fi is on here. Okay, so let me share my iPhone, and let's go to my screen sharing, and hopefully Zoom will come up here. Nope. Hold on, guys. I kind of started this little. Okay, it's having a little trouble, which will be very bad for our lab today. So at some point, I'm going to have to figure that out. Always technical glitches. That's my damn life these days. Let me try it one more time. Yeah, here we go. Okay, finally got it. Can you guys see my phone here? I want us to compare and measure the size of a sunspot, to the size of the sun, and see what kind of sense we can make out of it. So let me go here to function F5 and then to slide 3. Can you guys see what I'm seeing on my phone? Can you see my computer screen? Is that what you're seeing, Kayla? Yes?
Yep.
Yes.
All right. And you can see that ball of the sun there, right?
Yep.
So let's see. Let's hold my ruler up to it. Let's put the 0 there. Let's go right along the diameter. How many centimeters would you say that is? How many centimeters?
12.8 maybe?
7-ish.
12.7-ish, okay. And what would you say is the size of the sunspot in centimeters or millimeters?
About half a centimeter.
Pardon?
0.4.
Yeah, 0.4. Okay. Let's compare those two numbers together. Let's stop the share and let's go to speaker view. And let's try to figure out how big a sunspot is in comparison to Earth. Let's make a little scale model. So here's a ball that represents the sun. And the diameter that we just measured on the screen was 12.7 centimeters, right? And one of our sunspots was about 0.4 centimeters. The sunspot looks small, and it doesn't look like the sun is rotating very fast. But let's consider that if you multiply the sun's radius times 2, you get a diameter of 1.4 million kilometers. Now here's the question I want to ask the class. I want to know how big that sunspot is in kilometers, and I want to compare it to the radius of Earth, or maybe the diameter of Earth. For Earth, its radius is 6,400 kilometers, and its diameter, edge to edge, is 12,800 kilometers. How would I figure out how big that sunspot is? What would I do?
Would you multiply it against the ratio you have with the 12.7 centimeters is equal to 1.4 times 10 to the 6th kilometers?
Who's saying that?
Parker?
Oh, hi, Parker. Parker, that sounds reasonable. Can you just say it one more time? Because you weren't as loud as I wanted you to be.
Sorry, let me turn my gain up. So you would multiply it against the 12.7 centimeters over 1.4 times 10 to the 6th kilometers ratio you already have set.
I think you should try this instead, Parker, using dimensional analysis. Why don't you do this with dimensional analysis? What's your first step in dimensional analysis?
We'll write out what you're trying to transfer.
All right, so what am I trying to convert or transfer?
The 0.4 centimeters.
All right, cool. And what's my second step?
Multiplied by a division bar.
Okay, now third step.
Centimeters on the bottom.
Let's call them fake centimeters. I just don't want to confuse them with real centimeters. So I'll put centimeters prime on the bottom. That's my scale model. That's my model on the screen. And
Okay.
I'll put, as you said, kilometers on top. Okay. So what's my conversion factor?
It would be 12.7 centimeters on the bottom and then 1.4 times 10 to the 6th kilometers on top.
Do you see why I asked you to do it by dimensional analysis?
Yeah.
You'd had it upside down, right?
Mm-hmm.
Dimensional analysis helps us avoid those mistakes. Okay, so let's punch them up and see what we get. Anyone got a calculator can do that for me? I can check the work here. What'd you guys get?
I got 44,000
Units?
kilometers.
How does that compare to the diameter of Earth approximately?
Seven-ish times bigger.
Huh?
I got about 7 times bigger.
No. 12 versus 44? It's 3 or 4 times bigger. Right, Kayla? Okay. Do you guys see what my point is? My point is that this small looking sunspot is 3 times bigger than planet Earth. That's insane, right? Earth would fit inside this one sunspot 3 times. Perhaps that gives you a sense of just what a massive sphere we're talking about here. In retrospect, when I play the video, it sort of looks like the sun's rotating kind of slowly, but it actually must be rotating pretty rapidly because you're moving maybe, I don't know, 3 or 4 Earths per hour across the surface. And that's a pretty rapid speed. The video isn't playing well because it's being transmitted over the internet, so it's a little bit staggered here on my end. In fact, it's rotating almost imperceptibly here. In any case, the sun's big. That's my point, okay? We ain't talking about something small here. We're talking about a massive object, or a massive and a very gargantuan large object. So another thing that I'd like to do is kind of talk about some aspects of why the sun appears so magnetically active. Magnetic fields come from charged particles and plasma, and the sun certainly has its share of that. Let me show you guys a couple of other videos that are pretty amazing, if you ask me. If we go ahead here, we can see some a little video where they zoom in. Let me kill the sound. And they show you a zoom in of one of these magnetic fields causing a powerful eruption at the surface of the sun. So it turns out that the sun is magnetically active, and magnetic fields poke out of the sun at a variety of different angles, and the magnetic fields kind of get twisted up against each other because they interact with the plasma in complex ways. Here you can see Earth to scale, and you're basically looking at a plasma waterfall that is maybe 5 or 6 Earths tall. It's pretty dramatic there. And the magnetic fields are pushing the plasma up off the surface of the sun, and the gravity of the sun is causing them to kind of rain back down and slurp back down onto the sun. I'd like to give you guys a couple of basic rules for how magnetic fields are generated in hopes that it will help our discussion as we go forward today. So let's look at a couple of slides together. Magnetic fields, most people's experience with them are playing with magnets at the refrigerator, or maybe you've played with one of these horseshoe magnets. But in a physics sense, the basic way in which one generates a magnetic field is by sending a current of electrons down a wire. And all of the wires that are in your household items like lamps and television sets and even charging your cell phone, anytime you send a current of electricity down a wire, you actually generate a little magnetic field. And the magnetic fields have a very particular shape to them. They're circular shaped as the current of electricity flows down the wire. Let's take a couple of notes on that. I call these 3 rules for magnetic fields, and the idea is that it's supposed to help you build up intuition about why the sun generates so much magnetic field activity. Okay, so 3 rules for magnetic fields. And these are basic concepts that help account for the fact that probably not many of you have ever had a course in electromagnetism. So the first rule for magnetic fields is that moving charges create magnetic fields. So in your classic sense, you have a wire, and that wire might be made out of copper, and there are some free electrons in the copper atoms. And when you generate a current of electricity, you're actually pushing, sorry, I'm admitting more people here. You're pushing your current down this wire. And when you do so, a magnetic field is generated, and usually the shape of the magnetic field is in a circular pattern that sort of surrounds the wire here, okay? Now I'd like to show you guys a couple of extra slides. Moving charges make magnetic fields. And let's go back to this picture again. I want you guys to imagine with me that I would take a little wire and attach it to a battery, and then using a pair of needle nose pliers, I'm gonna bend the wire into an almost perfectly circular loop, so that now the electrons and the free charges are actually circulating around in a circle. And when you do this, the magnetic field, the circular magnetic field, forms around the loop in a kind of bunny ear pattern known as a dipole magnetic field. And dipole magnetic fields are very important in physics and astronomy because they appear in a lot of places. For instance, Earth generates a dipole magnetic field, and it has a constant shape that looks like this. This is the north magnetic pole and the south magnetic pole. What this means is that the Earth is spinning on its axis in a 24-hour period, and somewhere deep down inside the belly of the Earth, there must be a very hot, liquefied layer of metal, molten iron and nickel, that has enough free charges kicked off that those charges form a circular magnetic field. A circular current loop. And that circular current of charges gets sloshed around as Earth rotates on its axis, and that generates a planetary-wide magnetic field. Now, understanding the real formation of a geomagnetic field is very complicated, but that's a very simplified, basic concept. The sun would probably like to generate a dipole magnetic field for similar reasons, and that's as you go down into the belly of the sun, your neutral gas gets more and more ionized, and there's more charges, and those circulating charges, along with the rotation of the sun, can create powerful magnetic fields. The weird thing about the sun that makes it different from Earth is that the sun is not a solid ball of rock, but the sun is a goopy ball of gas. And the sun undergoes something called differential rotation. It doesn't all rotate at the same rate because it doesn't have to. It's a goopy ball, like tapioca pudding or something. And it turns out that if you measure it, as we will do in our labs today, the equator of the sun rotates with a period of about 25 days, whereas the poles of the sun rotate with a period of 35 days. And that means the equator of the sun is rotating faster than the poles. Now, what effect that has on the magnetic fields can be seen if we implement our second rule for magnetic fields and then our third one. So let's write down another rule here. Once you create a magnetic field, other charges like free electrons and free protons stick to magnetic fields. This is also very important for the ways in which we image the sun. Let's imagine that I had a magnetic field line poking out of the surface of the sun. The atmosphere of the sun is full of charged ionized particles like free electrons and free protons. In such situations, you can have an electron that has an extremely high kinetic energy. Sometimes the velocities of the particles can be a significant fraction of the speed of light. And when the electrons fly into and strike the magnetic fields, they get captured by the magnetic fields, and this causes them to sort of hit a wall, or it's as if you've slammed the brakes onto the electrons. And when they lose their kinetic energy, this can result in the emission of a very short wavelength, very high energy X-ray, whose energy is perfectly matched by the loss in kinetic energy of the electron. The Germans have a name for this. They call it Bremsstrahlung radiation. Bremsstrahlung radiation in German means braking radiation. As if you slammed the brakes on the electron and you caused it to emit a short wavelength, high energy photon. I can actually show you a little cartoon of this. If I go to my screen and I share with you guys one of those physics Java apps. Let's see if I can do that here. S drive, physics Java apps. Let's get a radiating charge. We can actually make a little model of this Bremsstrahlung radiation. Attempt to view the simulation anyways. Going to allow. Okay. Unfortunately here, oh wow, everyone keeps entering the meeting room and leaving. I don't know what's going on. Here you have a proton rather than an electron, but let's give it some velocity as if it was part of the corona of the sun and it had some very high velocity. Now, I can't show you the magnetic field. Everything good, guys?
Yeah, I'm struggling over here. My bad.
Is it some bad internet stuff?
Yeah, I had to call on my phone because my computer just keeps freezing. So my fault.
Samantha, you don't got to
Yes.
talk to me about technical glitches. That's the story of my life these days. All day long, I just fiddle with buttons and wires and knobs, and it always goes badly. So I just wish I've got to figure out. Oh, I can even see your face now. That's nice. Okay.
Because I'm on the phone.
I really got to figure out how to automatically allow you guys to enter the meeting so I don't have to keep clicking that button. That'll be better for all of us. Anyways, we're talking about this Bremsstrahlung radiation, and I'm going to get to why it matters in a moment. Let's imagine that this is a proton traveling in the atmosphere of the sun, and that suddenly it encounters a magnetic field, and the magnetic field captures this thing. I'm going to hit stop the charge. Can you guys see that little kink in the electric field line? That's a very short wavelength, high energy X-ray. And this is the Bremsstrahlung radiation. This isn't something that we learned about in chapter 5. This is called free emission. It tells us that even charged particles, when they are outside of an atom, can come to a short stop, and they can cause the emission of a very short wavelength X-ray. Now, why do I care about this, or why should you care about this? Because this explains what it is we are seeing when we look at the sun at non-visible or X-ray wavelengths. This is what the sun looks like at visible wavelengths, and you're looking at a layer of the sun called the photosphere, and this type of light is generated by the sun's temperature. It's essentially like a black body, like a hot glowing metal or a glowing coals in a fire. But when we look at the sun at different wavelengths, we see, this is seeing the sun at X-ray wavelengths. First of all, we're seeing a different layer of the sun. We're seeing its upper atmosphere. And the only reason you can see those magnetic field lines is because there's zillions upon zillions of electrons and protons, which are striking those magnetic field lines and then radiating X-rays back towards the camera. Basically, you're seeing that Bremsstrahlung radiation of charged particles interact with magnetic fields. That's nice because it allows us to see the corona of the sun, and it allows us to see what the magnetic fields are doing, which is quite interesting. Okay, let me get to my third point about magnetic fields. Not only do charges stick to magnetic fields, but also the corona, I know. Yeah, by the way, the corona, the virus, is named after the corona on the sun. Because if you look at a scanning electron microscope of the coronavirus particles, did you guys see those pictures of them? They have little protein spikes at the edge. Seen in an electron microscope.
Crazy. Yeah,
they're creepy looking, right? Seen from a microscope, it looks like the corona of the sun. So there's a reason why there's a connection between those two things. In any case, the third rule that I would like to institute for magnetic fields is that not only can charges stick to magnetic fields, but magnetic fields can stick to, or they can get twisted by, bulk plasma or bulk charges. And this is where we get to the reason why the sun is so magnetically dynamic and why there are all these powerful magnetic storms on the surface of the sun. Let me share my screen with you one more time. Oh, shoot. As soon as I try to, okay, hold on, bear with me here. Here we go. This picture, I tried to sort of put a bunch of different graphics together to show you what's going on. And what you can see is the sun is starting off as an ionized ball of plasma, at least in its interior. And there are a lot of free charges that are circulating and rotating around with the sun. But the sun's equator rotates faster than the poles. And the sun's equator begins to drag and pull the magnetic field lines along with it. After 1, 2, 3, 4 rotations, the magnetic field lines get so twisted up and convoluted on themselves that they begin to poke out of the surface of the sun at these wildly different angles. And as they poke out of the surface of the sun, they can drag plasma along with them, and sometimes even get so twisted up that they create these powerful bursts or eruptions in the sun, some of which are called solar flares, and some of which are called coronal mass ejections. Let's just for funsies here show you an epic coronal mass ejection. What can happen if magnetic fields just get totally out of hand? Watch this. Boom. That explosion, that eruption covered about half the sun's diameter right there. That was no small thing. That was an epic eruption. They call it a coronal mass ejection. I also have some older movies from a previous satellite called the Trace satellite, which can be worth looking at here. Let's go back to my S drive and look at sun movies from Trace. If you guys will be able to see this, this is a kind of classic video, lower resolution than the Solar Dynamics Observatory. Let's put it in loop mode if I can here. Now, take a look at what's going on in this video. You're seeing a powerful eruption on the sun in which magnetic fields get so twisted up that they cause this eruption called a solar flare. The solar flare itself is several times greater than the diameter of Earth. But solar flares do not achieve escape velocity, so much of the plasma gets slurped right back down onto the surface of the sun due to gravity. Here's a video of a coronal mass ejection by contrast. In this one, we can see some magnetic field lines poking out of the surface of the sun. Sorry, guys, this is not what I wanted. This is what I want. And what you can see here, can you guys see this? You can see my video here? Yes? Okay, thank you. The magnetic field lines get twisted up to the point where they create this powerful eruption, and basically a huge belch of gas and plasma gets kicked right off the sun. You guys will notice that a few minutes after the eruption, you can see some static hit the camera of the satellite here, and that static is evidence of something called the solar wind, a stream of ions and charged particles which travel through the solar system, smashing into the planets. The density of that plasma is very low, but over time it can have effect on planetary atmospheres. Jace, you have a question? Whoa, Jace, I'm having trouble hearing you here. Hold on, guys. I want to hide non-video participants. Trolls be gone. Okay. Jace, can you say that again? Jace, can you hear me? Jace, I can't hear you. So something funky. You're not muted, but I can't hear you. It's a day of technical glitches. You could always type it, I guess. I'm sure you had a very good question to ask. If you can figure out how to work your audio. Oh, you can hear me. Cool. I can't hear you, though. Did you have a question? I'm getting confused. Oh, the videos aren't exactly real time because they take place over several hours. So it would be a little boring. We'd have to wait, you know, because the sun is so huge, it takes a long time for stuff to happen relative to our, Samantha was mentioning we have short attention spans. That includes me as well and scientists. So I think what they're doing there is they're compressing time so that, you know, like 1 second is 1 hour or something like that. They record the videos in real time, and you could certainly watch them that way, but you'd have to have the patience to do it. It makes for a more interesting video if you compress several hours into a few, you know, maybe 1 hour per second, or maybe 5 seconds is 1 hour. I'm not sure what the conversion is, but I bet that's on the Solar Dynamics Observatory website. That's for sure. Okay, let's move on to a slightly different topic. Now we've got our rules for magnetic fields down, and that should help build up some intuition about how magnetic activity works in the sun. Let's think about the sun as a whole. The sun is a giant ball of gas. And I'm just checking my time clock here so I don't do what I did the other week. Okay, so let's go to share screen. And let's go to my slideshow. And I'd like to show you guys a couple of new slides here to think about how the sun maintains its shape. So check out this cute picture I have. Someone took a little image where it looks like they're holding the sun as a glowing orb on the sky. And this is a cute photograph, but I chose it for a reason. I chose it to remind you guys that we can see the sun with our naked eye on the sky, and it is a resolved astronomical object. Y'all are supposed to know the angular size of the sun. What is it?
Half a degree.
Half a degree. Clearly resolvable to the naked eye. And if you look at the sun, especially if you use some, you're not supposed to look at it with your naked eyes, but you can use a pair of these eclipse shades here. Not only are they good for eclipses, but sometimes they're just good for staring at the sun. Every now and then I'll just wake up and put a pair of these on and have my morning coffee staring at the pure orb of the sun. Oh, Ernie, question. Ernie, did you mean to raise your hand? I'm guessing that's a no. Okay. I've got a little, there's a little raise your hand button, and so it said Ernie raised his hand. I don't know if you had a question there.
No, I went to the men's room and the cat was on the computer when I came back.
That's awesome. Okay. All right. Well, that cat's also welcome. I forgot that this is Cat Crew. So in any case, why should the sun, oh, look at that guy. What's the name of that little bugger there?
Cinda. She's all white with a little gray spot on her forehead.
Oh, that's beautiful. Yeah, being able to see all your pets has been one of the untold joys of remote online learning. So let's take a think here about this concept, a very important concept in solar astronomy or in stellar astronomy called hydrostatic equilibrium. Well, Anna, if next time I see you, if I ever get to see you again in person, Anna, I can give you your very own pair of these so that you can stare at the sun all you want without going blind. Let's talk about a concept called hydrostatic equilibrium. Hydrostatic equilibrium is a concept that helps us understand why the sun maintains a fixed radius in space. It is a balance of forces between gravity pulling in and something called thermal pressure pushing out. Hopefully you guys can read that okay. It's a balance of forces between gravity pulling in and thermal pressure pushing out. And some people often phrase it as it is the answer to the question, why does the sun keep a fixed radius? And the more you think about that, the more you realize that that is a good question. Because if you have a bottle of perfume in a room and you open the stopper, you can smell the perfume molecules as they drift out of the bottle and through the room. If you watch your favorite science fiction movie or science fiction TV show, and they put someone in an airlock to space them, and you open the airlock in outer space, the air goes rushing out into the void of the vacuum, sucking every person or space alien along with it, right? Now, we've learned this because, you know, we watch a lot of geeky science fiction shows, and we also had some experience in everyday life. But the sun is just sitting there in the vacuum of space. If you think about it, why shouldn't all those gas particles just blow away, or at least just vary from time to time? There are a class of stars, by the way, that do not maintain hydrostatic equilibrium. These are the so-called variable stars, whose radii pulsate and oscillate like an accordion. But not our sun. Our sun doesn't pulsate. It maintains a perfectly fixed radius that stays exactly 0.5 degrees on our sky at all times. It's because of the competing tug-of-war between gravity pulling down on all of the gas atoms and the internal thermal pressure, the pressure generated by the motions of the atoms that are pushing back out. And here, when we talk about thermal pressure, we really have to refer to something particular, the ideal gas law, so that we can understand what pressure is. Class, I'd like to erase here, so shout at me if you haven't finished your notes yet. Here I go. Okay. So let's talk about thermal pressure. Thermal pressure can be related to something called the ideal gas law. And the ideal gas law explains how a system of particles interacts with each other in a closed box. Let's share my screen and see if we can find a picture of the ideal gas law. Here you go. Here's a model of the atoms inside the sun bopping around with each other. Since the ratio is roughly 3/4 hydrogen to 1/4 helium, we can assume that the blue pellets are like hydrogen atoms and the red pellets are like helium atoms. And you can see they all have kinetic energies and they're bopping around together. The ideal gas law is a relationship between 3 parameters of a gas. If you ever took a chemistry class, you might have learned it as PV equals nRT. Back in my day, the kids used to call it PivNert. But PivNert is lame. That's for weak sauce chemists who don't understand how real science works, okay? Just kidding. Love chemists. Some of them know science much better than me. Sorry, I'm trying to focus my camera here, and I'm having a hell of a time. There we go. Okay, the physicist's way of describing the ideal gas law is pressure equals NKT, where P stands for the pressure of the gas, measured in units called pascals, and we'll talk about that in a moment. N is the so-called number density of the gas, measured in a kind of funky unit called particles per cubic centimeter or particles per cubic meter. K is a constant of nature called the Boltzmann constant, 1 × 10⁻23 joules per Kelvin. This is a new constant of nature that shows up anytime you deal with with gases. And lastly, T is the temperature measured in Kelvin. Hey class, how did we define temperature in our chapter 5 lesson? What was our definition of temperature? Oh, it would be so nice if someone would interact with me. Then I wouldn't feel so alone during this quarantine period. How do we define temperature? Are there any enlightened science students out there?
Didn't we define it as heat?
No, we very much did not. We said temperature and heat were different concepts. Heat is a transfer of energy. Just a science student here, not enlightened. Well, enlighten yourself by looking at your notes then. Anyone? Kayla, Jace, save me, someone. Oh, I'm sorry, yeah. That's right, kinetic energy of the particles. Oh, that's right, Jace doesn't have a microphone anymore. Yes, Jace, it's the kinetic energy of the particles, okay? So let's redefine that up here. If the temperature is the average kinetic energy of the particles, how should we understand pressure, this new concept? I'm going to erase class. Pressure, defined in a physics sense, is defined as the force of the gas particles over the unit area that they are striking against the walls of their container. And usually the picture you have is of some wall, like this could be the rubber membrane of a balloon. So this is your wall. And then you've got some gas particles, hydrogen or helium or whatever you like. And these particles are slamming into the walls of the container and delivering some force per unit area against the walls of your box or your refrigerator or your rubber membrane. Or you don't even need a wall to define pressure. It could be the force of the particles smashing into each other. Now let's think about the units of pressure. In the MKS system, forces are measured in newtons, and area is measured in square meters. And a Newton per meter squared is defined as a Pascal. Let me try to write that a little neater for you guys. So pascals are the MKS unit of pressure. Just as a sort of side comparison, air at sea level, the air that you're breathing right now, has a pressure of 100 kilopascals, or 100,000 pascals. Let's think of some other units of pressure. How about when you go to pump your tires up on your bicycle or at the gas station? What do you usually inflate your tires to? What units are you using in the imperial system?
PSI.
PSI. And do you remember what that
Pounds
stands
per
for?
square inch.
That's right. So in the imperial system, PSI is pounds per inches squared. And I think it's something like 14.7 pounds per inches squared is the pressure of air at sea level. When you inflate tires in your car, you might inflate your tires to 300 kilopascal. I don't know what 3 times 15, I guess 45 pounds per square inch. Now, other units of pressure that show up from time to time, especially in this class, in planetary science, we sometimes use atmospheres. 1 atmosphere is about 100,000 pascals or 100 kilopascals. And atmospheres bear a close resemblance to another unit used by meteorologists. Atmospheres are very close to the definition of a bar. So depending on who is talking about the pressure, you'll hear a variety of different units. When you talk to your auto body mechanic, they're going to say, oh, PSI. When you talk to a planetary scientist, they usually measure them in atmospheres. When you talk to a meteorologist, they might measure pressure in bars, and a physicist will measure them in pascals. But all these units can be converted between each other. Obviously, there is a relationship between pressure and temperature, and the ideal gas law tells us what it is. In fact, I've got a cute little app for that. Let's take a peek at that. Let's exit out of here for a second. Let's go back to those physics Java apps if I can find them. And we have some gas properties. Here we go. I know I'm sort of running out of time here, so try to get through this quickly. I just want to build up your intuition about pressure. Okay, so here's my little box of gas. It says pump the handle. Let's pump it up. Pump, pump. Here come the gas particles, and they're bopping around inside my box. Notice that they've decided in this animation here to measure the pressure of the gas in atmospheres. So here we're currently at 300 Kelvin, which is close to room temperature, 293. And the pressure is just slightly less than the typical pressure of air in our rooms, which is 80% of a planetary atmosphere. So what's going to happen if I add some heat to my gas? What will happen to the temperature? What will happen to the pressure, students?
It would increase.
Yeah. Let's add some fire, and let's watch those particles move faster. And obviously, as the bullets move faster and faster, the pressure that they exert on the walls of their container gets higher and higher. Now I can add some ice. Let's chill that gas right back down again, and you can see the pressure and the temperature dropping. Now, if I take Mr. Robot here and I squeeze the gas, what do you think is going to happen to it? If I take this wall and I squish it and I compress it?
Pressure's going to increase.
Yeah, what about the temperature? Chris, I agree with you. What about the temperature? It will also increase. Let's watch it go. Woo, doggy. Look at that thing go. What property of the ideal gas? Oh, I blew the lid off this sucker. What property of the ideal gas law am I changing when I compress the gas?
Area.
Pardon?
Area.
But area wasn't one of the variables. Let's see what the chat, oh, I can't read the chat in share mode. Sorry, Jace, you're voiceless. Not area, but P equals NKT. Which one are you changing?
Jace said N.
N, the number density, because you're, oh yeah, oh, I like it, Jace, thanks. You're compressing, if you compress the volume of the gas like you do in a piston, right? You're changing the number density because it's the same number of particles, but the box is now smaller. So the number of particles per cubic centimeter or per cubic meter go up. Hey, by the way, there's another feature of this where I can add some gravity. What do you think would happen if I added some gravity to this gas? What would happen to the temperature, to the pressure?
Both would increase.
That's right. It's the same as squeezing the walls of the container. And that's hydrostatic equilibrium. Watch this. Woof. Look what happened to the temperature there. It skyrocketed. In fact, I can even open the lid of this container. And this is kind of like what's happening with the sun. There's sort of a version of hydrostatic equilibrium here, where the gravity is trying to compress the gas particles down to the bottom of the box, but their thermal motions add pressure, which kind of, that prevents the atoms from all collapsing into a single flat line at the bottom. And this is a version of hydrostatic equilibrium right here. Except our version keeps the sun in a perfect balance. By the way, notice that the temperature of the gas is quite high. Any gas that reached a temperature of 1,000 Kelvin would actually start to glow like a black body at visible wavelengths. So you should know that just by squeezing a gas, the sun can actually shine light just by squeezing itself down. Whew. We're getting close to the end of our lecture here. I just want to do one last thing. I'll probably start off next time talking a little bit about energy methods in the sun. But if you guys would do me a favor, before we end class, let's do one last little set of notes here. I want to just take some notes on the layers of the sun so that we can refer to them in our homework next time. Actually, you know what? No, scrap that. I got a better idea. We'll save the layers of the sun for next time. So next time, I want you guys to put these two notes for me, because I'm probably going to forget everything between now and Wednesday. And here's what I want to do next time. I want to do energy methods of sunlight. And I want to do layers of the sun as well as some other things. But if you can tell me to start there, that'll help get me going on Wednesday. Does that sound good, everyone? All right, I'm seeing lots of thumbs up. So I'm definitely trying not to make the boo-boo that I made with you guys the other week where I talked over time. So I heard you, Matthew, loud and clear. Okay, so let's talk in gallery view about what our plan is. Our plan in a few moments, no, that's okay, Matthew. I got some personal stuff to do too. Okay, anyways. We're going to attempt to do a lab on rotation of the sun, where we track sunspots across the surface of the sun, and we use that to calculate the sun's rotation period. It's a pretty simple and easy lab, and if you want to get the maximum benefit from this, let me tell you what you're going to need to do it. We'll probably take a little 5-minute break just for me to get some iced tea, but I want to tell you what the materials that you're going to need for the lab are so that you can kind of prep for it while we take our 5-minute break. As I mentioned at the beginning of today's class, if you go into Lab 8, Rotation of the Sun, I have provided you guys 2 sheets. One is the data sheet that you're going to work on. Actually, there's supposed to be 3 sheets. Did you guys only get 2 sheets there? Holy smokes.
Well, if you look on the backside, if you have the book at least, it has the other sheet, I'm pretty sure.
Yeah, I'm worried that
Spot
some
C.
people might not have the backside. And in my other class, I included the 3 sheets, but I think your class was the first one I was trying out. I was trying stuff out for, so I think I missed the 3rd sheet. Hold on, let me. When you guys click your sunspots lab, this is what you see. You got this. Yeah, you're missing. You guys are missing the 3rd page, which is 13-6. Okay, I can fix that right now. How can I fix that? I can go back. Rotation of the sun, and I can edit it if I can find where I put those damn labs. Browse my Sunspots Lab 1. Browse my computer. Oh boy, where did I put the labs? Lab, Astronomy 1020, Sunspots Lab. I think this one has all 3 sheets. So let me go back here. Sorry, I can't. Your faces are blocking the submit button. Submit. Blackboard is extremely clunky. Sometimes it just fails here. Oh, there we go. Okay, guys, let's see what happens if we click the other Sunspot Lab. Yes, this has all of the pages. So now you can print 13-6. So I'm going to hit print on my computer here. And I just want custom, I just want page 6 because I have the other 2 printed already. And it's going to give me some crap. Okay. So, all right, now that's printing up. So let's get back to the talk here. So you're going to need your 3 pages. You're going to need your sunspots. You're going to need 13.5 and 13.6. And let me show you some other things that would help this lab go forward. Obviously, you're going to need your pencils and your calculators. I borrowed a compass from the lab and a protractor from the lab. It'd be real nice if you guys had one of those. Show of hands to the people I can see in the video chat here. How many people have such materials?
I have to go and check.
Okay. If you don't, that's fine, but what you're going to have to do is try to freehand it. And okay, Anna, I see you. All right, so this is as I thought. No one's got protractors and compasses. Apparently, you guys aren't hardcore enough geeks to party with me, okay? You got to bring your own supply, man. Okay, anyways, if if you have one of them, bust it out. If not, you're gonna have to try to freehand this with me, okay? In any case, okay, well, Matthew, that's why I have the handouts attached to the Blackboard. By the way, if you're really hard up and you don't have a printer, you might have to try to draw this out by hand on a page and follow along there. That's if you have neither lab book nor access to a printer. But somehow we got to do these classes remotely. I'm doing my best, right? I can't fly to your house and like give you handouts, or I would do that. So can we wing it? Can we make this happen together? All right. So let's say right now the time is 12:58. Shoot. Let's take a 5-minute pause, and then I'll get some iced tea, and we'll come back and we'll hit this. Sound good?
Real quick, does like just using it like a program on my computer instead, like just opening the PDF work as well?
Yeah. If you can open this up, your PDF, and you can use Photoshop or Illustrator or even MS Paint or something like that, you can do it all digitally and then submit that. That's totally okay. Okay. I'm going to just temporarily stop recording so that I have the lecture separate from the lab.